Hi, everyone. We're finishing up lesson 25 on confidence intervals for population parameters. Leaving this simulation here, also bear in mind that we can sort these. So these are the most recent 100. We could sort these by their sample proportions. We can see the bad ones at the top and at the bottom, in fact. Right. We could do it again. Sample, sort. We have a bunch of bad ones here on top, a bunch of bad ones on the bottom here. And actually, if we had a histogram for the sample proportions for all 2,000 or so confidence intervals, if we could actually get a histogram for that, we could probably figure out a 95% confidence interval just from this simulation. If we had 2,000 confidence intervals and their sample proportions to look at. Together, the middle 95% of sample proportions might form a good confidence interval for P, 95% confidence interval. This is a key idea behind the bootstrap, the idea of using simulations to develop confidence intervals. In which case, have a bunch of simulations. Maybe you don't have to know that much theory. Run a bunch of simulations and look for the middle 95% of sample proportions. All right. Now, back here, about 95% of these contain the true value for mu or p, the population parameter, for a 95% confidence interval, but about 5% will fail. Again, statistics predicts its own failure rate. This failure rate we refer to as alpha. And the confidence level is the complement 1 minus alpha. So, for example, the standard confidence level is given by 95%, or 0.95 as a decimal. So the value for alpha is the complement, 1 minus alpha. Okay, so 1 minus alpha is 0.95. The complement of this is just alpha, which is 0.05. 0.95 and 0.05 are complementary probabilities. They add up to 1. So if there's a 95% chance that a confidence interval contains mu, then there's a 5% chance it doesn't. This notation for alpha, we're going to see later on. It corresponds to the probability of us basically failing. It's the probability of us basically failing, as we'll see when we get to hypothesis testing in the last part of the class. Okay, now let's compare confidence levels. You might argue, well, why don't we get a 100% confidence level? Why not get a 100% confidence interval? Well, what impact would that have on the confidence interval? So let's say I have two interval estimates, and they're both centered at the sample mean, x bar, from a sample. And we want to estimate mu, a population mean. Again, these are both interval estimates, symmetric about the sample mean. Which one of these is more likely to contain the true value for mu? The smaller interval on top or the wider interval on the bottom? Imagine a shooting range. If you're at a shooting range and you're trying to hit a target, they're both centered at the same place. How are you more likely to hit the target? If you're shooting a wider swath of bullets or a thinner swath? That's a more violent example or analogy. Well, you're more confident that the interval contains mu if it's wider. So we associate wider confidence intervals, assuming that they're all centered at x bar. If it's out here, well, that's not too good. But if you have interval estimates that are all centered about the sample mean, then the wider one is more likely to contain mu. But that leads to a trade-off. So confidence levels and trade-offs. Based on the same sample data, we can use different confidence levels, for example, 95% versus 99%, to construct different confidence intervals, a 95% CI versus a 99% CI for mu, or some population parameter. Again, which is usually more likely to contain a population mean, a wider confidence interval or a smaller one. Again, assume that they're both symmetric about the sample mean. They're both centered at the same place. Well, a higher confidence level, like 99%, will lead to a wider confidence interval. So for example, up here, if I told you that one of these was a 95% confidence interval for mu, and the other was a 99% confidence interval for mu based on the same sample data, well, the top one would have to be the 95% one, the thinner one, and the wider one would have the larger confidence level, 99% or 0.99. So again, the 99% confidence interval here is more likely to contain mu than this thinner 95% confidence interval, and they're both centered at the sample mean. Again, the same is true for p hat and p. A higher confidence level will lead to higher reliability. This 99% confidence interval is more likely to contain mu, but it's wider. It has lower precision. Now, you may not appreciate what this all means. Let's put this in the context of students asking about test scores. So forget about this whole thing about means. Let's go back to the general idea of confidence levels. So if you were to ask me, Professor, could you give me a 100% confidence interval for what I did on the test? Let's say the test was scored out of 100 points. What's the only answer I could give you? The only answer I could give you is from 0 points to 100 points, assuming no extra credit or anything, and no negative scores. Let's say I'm not super cruel. But if you were to ask me, give me a 100% CI for how I scored on the test. Well, there you go, 0 points to 100 points. You agree that's correct. You're absolutely sure this contains your score, but are you going to thank me very much? Well, probably not. This only tells you how much the test is worth, or what the maximum score is, right? Maximum possible. It doesn't tell you how you did. This just tells you that on the test, you could possibly score between 0 points and 100 points, but I'm not really telling you how you did at all. I'm telling you nothing about how you did. You have no idea if you got an A or an F. So let's say you go, okay, you're being very reliable, but not very precise. So again, this 100% confidence interval is reliable, but not precise. So let's say you ask me to give you a more precise confidence interval. And I tell you, okay, I think you scored between 78 points and 82 points. And you go, wow, that's pretty precise. I feel very good about my knowledge about how I did on this test. You're telling me I scored between 78 points and 82 points. How sure are you? It's that who wants to be a millionaire question. How sure are you? And I tell you, I'm 10% sure. I'm giving you a 10% confidence interval. So here, I'm being very precise. I'm giving you a very thin swath of numbers, a very thin swath of scores, but, so it's very precise, right? I'm being very precise here, but it's not very reliable. There's only a 10% chance that you're in here based on appropriate methods, whatever that means. So there's a trade-off between reliability and precision. And again, the classic trade-off is 95%. That's the standard. 95% is the gold standard. That's the typical trade-off we have between these two issues, between these two tensions of greater reliability versus greater precision. So very often I'll ask about 95% confidence intervals, but not always. I reserve the right to ask about other confidence intervals as well. Reliability versus precision. You can't get everything in life. Later on, some more lessons in statistics.